Last time we looked at the definition of enthalpy. We proved that enthalpy, the change in enthalpy, delta H, is equal to the heat at constant pressure, Q sub P. We discussed how we could measure the change in enthalpy directly by doing a calorimetry experiment at constant pressure. Okay, that's not always the most convenient way to get a value for delta H. In particular, that requires that you actually do the reaction in the laboratory. Some reactions, as you might imagine, are difficult or impossible to get to go as you would like them. There's other ways to get values for delta H, and that's what we're going to take up now. So main topic for this segment is what are called heats of formation, or the standard molar enthalpy change of formation in more proper terms. Okay. Having a table that just lists delta H for every possible reaction would be kind of an impossible task, right? Because just think about the number of reactions that we've seen already this semester that have O2 in them, right? And so if I had to have every one of those reactions there for every possible substance, it would be an exhaustive and incredibly large list that no one could ever really assemble. But delta H is a state function, and that means we can get useful information from a reasonably small amount of data. Essentially, there's a system that people have sort of worked out and agreed upon says we tabulate one value for each chemical substance, and we can use those to calculate the enthalpy changes for any reaction that's of interest, okay? The quantity that is the most commonly tabulated for this is something known as the standard enthalpy, or standard enthalpy change of formation, okay? So in this symbol here, there's delta H, that's the change in enthalpy. The F under there, that stands for formation in this context, okay? This little superscript degree sign thingy, that is a reference to a particular definition of the way in which those values are determined, the so-called standard state convention for those heats of formation, all right? And we'll talk about what that is in a moment. So, gosh, a shorter moment than I thought. So the standard state of an element is defined for thermodynamic purposes as being its most stable physical form at 1 atmosphere and 25 degrees Celsius, essentially room temperature, okay? So if you think about, there's a lot of substances where you actually would know what the standard state is, right? For oxygen, the standard state is O2 as a gas, right? Because oxygen at 1 atmosphere pressure and 25 degrees C, that's the state it's going to be in, right? If I looked up water, H2O in the table, the standard state should be that it's a liquid, because that's what water would be at 1 atmosphere pressure and 25 degrees C, right? There certainly are elements and compounds where you wouldn't necessarily have any idea what the standard state would be, and there's ways to find out what those are, which we'll also talk about. So we tabulate all the enthalpies of formation with respect to that standard, okay? We make a definition for the enthalpy for an element in its standard state, and then we use that as a reference point, okay? It's a little bit like anytime you calculate energies in a physics problem, right? You get to pick where a zero of energy is. Here we're picking a reference that is based on this idea of that being the standard state. So to have a heat of formation, the first thing we have to do is define what is known as a formation reaction. These reactions, honestly, are often somewhat hypothetical, to be clear about it, but nonetheless, they're useful, okay? So the formation reaction has a very specific definition, all right? It says on the left-hand side of the equation as reactants, we have elements in their standard states, okay? So everything has to be just an element. There can't be any compounds there. And on the right-hand side, we want to have just 1 mole of whatever compound we're trying to make, okay? And so I'll put up some examples of some of these formation reactions in a moment, and you'll be able to see what they might look like. But that reaction, whatever it might look like, the enthalpy change for that, delta H for that formation reaction, making 1 mole of the substance from elements in their standard states, the delta H for that is what is defined to be the heat of formation, or this delta H sub F with our little degree sign on it there, okay? In ordinary talking about these things, people always just call this the heat of formation. Right. The table might say that it is officially something like the standard molar enthalpy change of formation, but anybody working with them just says it's the heat of formation. Okay, and that's the phrase I will most likely use in all future references to these things. Okay. Because of the way that definition says that the elements have to be in their standard states and we can only have 1 mole of the compound on the right-hand side, that means some of these reactions are going to look a little bit weird by the standards we set out with when we started writing chemical equations, okay? Hopefully we're familiar enough with chemical equations that won't bother us too much at this point. So here are some formation reactions, okay? Carbon's actually one of those elements where you might or might not guess correctly what the standard state is. The standard state is actually graphite. Graphite is slightly more stable than diamond at room temperature. But if you have any diamonds, don't be alarmed. They're not quickly going to turn into graphite. That process takes approximately forever. But graphite is the standard state. So if I wanted to make the formation reaction for methane for CH4, I'd say I need 1 mole of graphite, just written as carbon, that's just the C. I need 2 moles of hydrogen gas, H2, because that's the standard state for hydrogen, right? I know that at room temperature and pressure, hydrogen will be H2 gas. I make 1 mole of methane. That one looks perfectly reasonable. The couple under that look a little bit less reasonable, again, at least in terms of the way we set out to have rules for balancing equations, because you'll notice they have fractions on the left-hand side. That gets forced to happen in a number of cases because we have this restriction that says we can only have 1 mole of the stuff on the right-hand side, right? So if I want to make ammonia, NH3, that says I need just 1 nitrogen, right? The standard state of nitrogen is N2. So the only way to get 1 nitrogen out of N2 is to take a mole of N2, right? If I think about the coefficients as being moles, then it's not so bad that they're fractions, right? But in any case, the sort of ugliness of having the fractions in there is offset by the fact that having it always make 1 mole of the stuff is crucial to how we're going to use these data. Okay, the one on the bottom is for NO2 gas, right? And so in those cases, we've got nitrogen, N2, hydrogen, H2, oxygen, O2, all as gases. Those are standard states that you would probably be able to guess if you had to, right? Because you're kind of aware of what the normal form of those things would be. So 1 mole of products, so we can sometimes have to put fractional coefficients in there, okay? That's the only way to get to have only 1 mole of products, right? In that second and third equation, if I wasn't gonna have fractions, I'd have to multiply everything through by 2 to clear the fractions, but then I'd have 2 moles of the compound on the right. Can't do that, right? Notice there's not a rule that says the thing on the right has to be an element or has to be in what you might consider its standard state, its most stable physical form, right? It can be in any form because we want to be able to write the formation reaction for anything in any state. All right. So there are tables of these heats of formation. There's one in your textbook. If you are looking in a print version of your textbook, it should be in Appendix E. There's also some other columns in there for other things. If you're in the ebook, anywhere around where it's talking about this stuff, there should be links to a version of that same table. What I've done for our purposes here is just to grab onto a little slice of the table. So these are some values from the table that is in the textbook, okay? In the textbook, and in most places where you'll see these tables, the substances are broken down, they're separated out by elements, essentially. There's not any kind of hard and fast rule about how you decide which element a compound is going to be under, right? So if I was looking up water, H2O, if I looked under hydrogen and it wasn't there, I would just go look under oxygen. Okay, it happens to be under hydrogen in our list, but it's not certain it would be there in everyone's list. Okay, that's a little bit awkward, but that's just how it goes. So what do we see here? We see that the values for these things are listed in kilojoules per mole. We can see even from this little slice that some of them are positive, some of them are negative, and in fact, some of them are 0. They tend to be on the order of hundreds of kilojoules per mole, give or take. Right? They could be, they're not going to be tens of thousands. They're not going to be, like small fractions in most cases. They're going to be typically on the order of tens or hundreds of kilojoules per mole. Let's start by looking at the one that is 0 here. Notice that that's the formation reaction for H2 gas, right? Based on what we just said about what the formation reaction is, let's think about what that reaction would be, right? It would say that I have 1 mole of H2 gas. That's the thing I want to make. So on the right-hand side, I have 1 mole of H2 gas. On the left-hand side, what do I need? I need elements in their standard state. Well, H2 gas already is an element in its standard state, right? So if I wrote a formation reaction for hydrogen gas, it would look like that. It would say H2 gas basically does nothing. It just becomes what it already is, okay? So delta H for that and delta, the change in anything for that reaction would have to be 0. This points to a way to figure out what the standard state is if you don't know. If you wanted to know what the standard state of carbon was, for example, if you looked in the table under carbon and just looked for what form has a heat of formation of 0, that's your standard state. Right? So if you looked up carbon, you would see that graphite has a heat of formation of 0. Diamond has a small positive heat of formation, okay? And so any element you look for, you could find the standard state by doing that, Notice I put in here, this is liquid water, this is steam, and notice that those two have different values, okay? That's a source of many errors in students working problems that are based on using these data. So if you're looking up the values to work a problem, be really careful and go a little bit extra slow and make sure you're getting the right numbers, because I can tell you, having watched a lot of students work a lot of problems, if the first time you go look up the number, you grab the wrong one, it'll be a lot of tries trying to do the math and the problem before you go back in the table to find out if you just got the number wrong when you copied it down. Okay. On the bottom, for some reason, I included hydrogen peroxide, so whatever. Notice that hydrogen atoms here, that has a positive heat of formation. That formation reaction would say I need an element in its standard state over here. So I have H2 gas on the left-hand side, but I only need one hydrogen. So I'm going to put a half there. And then I have hydrogen gas here, right? So that formation reaction corresponds to breaking the hydrogen-hydrogen bond in H2. We know that has to require an input of energy, right, from everything we said about bonding. So it should make sense to us that that value has to be positive, right? The ones that have negative heats of formation, that says that formation reaction would be downhill in energy, right? It would be releasing energy if we turn the elements into those compounds, okay? And so as you work with these, you'll see more of the values and you'll get kind of used to how they range. But that's a decent little, just a quick tour of what are some of the things we can see for those values and what to watch out for. So if we want to use these heats of formation, I said the point of these was to be able to calculate delta H for something approaching any reaction we can think of or dream up and want to do, okay? This is the combustion reaction for glucose, I guess. We figured out we did a calorimetry problem for this reaction where we found delta H for it in a recent video, right? Now we're going to find delta H for doing this same reaction. Okay, I'm going to imagine a pathway for my reaction. I'm going to imagine a different pathway now than I have before. I'm going to say, imagine that the way the reaction takes place, and this is a crazy pathway, there's no way this is what really happens, but imagine that my glucose just decides it's going to first turn into elements in their standard state. So it's going to make some graphite and some hydrogen and some oxygen. The oxygen here already is an element in standard state, so it won't have to do anything. Then I'm going to take that collection of elements in their standard states and react them to make the products, okay? That would get me to the right product. So it is a possible path. And if I can find delta H for that pathway, it'll be the right delta H, even though it's a silly, unreasonable and unphysical pathway, okay? So we're exploiting the fact that H is a state function. All right, I'm going to belabor the point of how this works. And then at the end of this video, we'll get you to a nice, simple, and easy to use equation, I promise. So here's my reaction. And let's look at how this pathway would go. I usually don't like to do these pop-in things, but I think it's handy for this. If I take my glucose and turn it into elements in their standard states, I'd get 6 moles of graphite. I'd get 6 moles of H2 from the 12 hydrogens, and I'd get 3 moles of O2 from the 6 oxygens, right? The 6 O2 and the delta H for that would just be, I'm doing the formation reaction backwards. For the O2, it already is an element in standard state, but anyway, I could still call that doing the formation reaction, right? And I get that. Now I can grab up the elements I need to make the products, right? So let's take the 6 carbons and those 6 oxygens on the right and imagine reacting those to make 6 moles of CO2, right? Obviously, there's no difference between those oxygens and the others, but I picked a reaction where I could make the coefficients work to do this and have it work itself out, okay? Then my remaining elements that are still there, the 6 hydrogens and the 3 oxygens, that's just what I need to make the 6 moles of water, right? So I have 4 steps in here. I can imagine this taking place, do step 1, do step 2, step 3, step 4. If I know the delta H's for all 4 of those steps, I just have to put them together to get delta H for the whole reaction, okay? Every one of those steps there has a heat of formation that's either the heat of formation of one of the substances or it's minus the heat of formation, right? Because the ones that are steps 1 and 2, those amount to doing the formation reaction, but doing it backwards, going from the glucose to the elements in the standard states, okay? When I make the CO2 and the water, those amount to doing the formation reactions forwards from the elements to the compounds. Okay, so steps 1 and 2, the heats of formation for those would be minus a delta HF value. For steps 3 and 4, it would just be the delta HF values for those. And that leads me to a way to put these things together, okay? So in general, my reactants, I'm going to have minus the heat of formation for those. The products, I'm going to have the heats of formation for those. And that means my delta H for my reaction There's a pretty version of this equation on the last slide in this stack, but it's going to be the sum for the products of the number of moles that we have times the heat of formation for each one, minus that same sum for the reactants. And right now I can just feel some of you crying out that when we did the one with the bond energies and we did a problem in class, I told you that that one had to be the reactants minus the products, okay? This is the first of several equations that I referred to that are gonna make you feel like that other one must be wrong. It isn't wrong, but in most cases, in all the other cases, we're gonna do something like this where we take the sum of stuff for the products minus the sum of stuff for the reactants. So let's do an example, and then we'll rerun that equation for us. So here are some heats of formation from a suitable table. The information for glucose is large and negative, 1274 kilojoules per mole, but glucose is a relatively large molecule, so that's a little bit, that's not troubling really, right? CO2 and liquid water are values there. Those are very common values. Gosh, embarrassingly, I kind of just know those numbers because I do these problems too often. You would no doubt need to go and look those up in the table because you're more normal humans and don't spend your entire life doing chemistry problems. So I'm envious perhaps, but let's do the problem. So here's my reaction. And taking my equation says delta H for this thing should be equal to delta H. Let me just call this delta H for the reaction, just so we're clear about what delta H we're talking about, right? This should be the sum for the products. So that should be 6 times the heat of formation for the CO2 plus 6 times the heat of formation for the water minus the same sum for the reactant side. So that's the heat of formation for the glucose. And for completeness, let me say minus 6 times the heat of formation for the water. Not the water, the oxygen, sorry. That last one's going to be 0, so it won't make any difference numerically if I leave that out, okay? Grabbing the numbers that were in the previous slide, this is equal to 6 times minus 393.5, and I'll talk about units separately afterwards. Plus 6 times minus 285.8 minus 1274.5 minus 6 times 0 for that last one, okay? Notice that when we do these things, we have a string of terms here. They've got positive and negative values and positive and negative signs. There's a lot of ways to mess this up, right? And so it's important that you really take your time and be methodical, putting numbers in your calculator or whatever to get through the calculation, okay? There's a lot of different ways to flip a sign anywhere in there in that collection of minus signs and get a totally different number. Okay, my notes tell me if I measure this out that if I calculate this out rather that I get minus 2801, which I believe is a larger negative number than we got when we calculated delta E. And now let's talk units, okay? In these quantities, those numbers in front, remember my sum was for N, the number of moles, times the heat of formation, right? So that 6 is, in this case, that's the water. So that's this 6 here we're looking at, but that has units of moles. The things in parentheses all have units of kilojoules per mole because that's what it says in the table when we look them up, right? So my value comes out with units of kilojoules. That means if I do exactly what that equation says, I would release 2,801 kilojoules of heat, right? That says if I were to burn 1 mole of glucose, I would get those 2,800 kilojoules. But to get that same amount, I need to use 6 moles of oxygen or make 6 moles of CO2 or 6 moles of water, right? So the main reason why we don't put that as a kilojoules per mole thing is if we do that, then it's kilojoules per mole of reaction, like for the equation as written, right? So one way to think about this is that if you, it's a minus sign, which means the energy is being released, you can think about those 2,800 kilojoules as essentially being a product of the reaction, right? And then you could do like a mole to kilojoule ratio that would say if I burn 2 moles of glucose, I'd get twice that much, minus 5,600 kilojoules, right? If I burned 1.5 moles of glucose, I'd get halfway between those two numbers. So I'd get something like 4,200 kilojoules of energy being released, okay? These problems are not hard. If you just look at them, it's literally just adding and subtracting some numbers that you look up in a table. There are a lot of ways to mess them up, okay? So just try to be extra careful, because once you start messing it up, you just get more and more frustrated, and you have to recheck that you looked up the numbers correctly and things like that. And it's often difficult to watch. So this is just, I wanted to include a nice looking version of the equation, okay? So this is how you will use that equation. Whenever you use that equation, honestly, you're never gonna really think about the idea that says, I'm taking the reactants and turning them into elements in standard states, then I'm turning those into the products, okay? But I think it's worth at least one time walking through that to see how this equation comes to be. Right? The ends there, those are the number of moles that balance the equation. Right? So I take the sum for the products of number of moles times heat of formation minus the same sum for the reactions. Do that, and I will get delta H for the reaction. So you can find delta H for any reaction as long as you can find the heats of formation for the various things that are in the reaction, right? And you can find a lot of different things. There's a lot of them in the table in the book. There are sources for more extensive listings. One of those is the so-called NIST web book, which is where I go when I need those values to actually put things in the table for the textbook. I look them up. NIST is our US standard of authority on all things data-oriented for sciences, pretty much. And so they're the go-to source for those values, at least for me.